Okay, so to find the rotational inertia for a solid cylinder, we will first start off with the basic inertia formula, which is I is equal to the integral from r squared, the distance away from the pivot, with respect to mass. But we can't do that because different masses have different radii away from the axis of rotation, so you can't do that. So we have to find a replacement for dm, right? So we're dealing with a 3D shape, so we know that it is uniformly dense, so rho is equal to mass over volume, right? Then we can expand this into mass over the area of this cylinder, which is a circle, times the length, which give you volume. So we can rewrite it with respect to m. So m is equal to rho al, right? So we're trying to find the derivative of mass. So dm is equal to rho is a constant, right? The density doesn't change, so that's the same. Then the length of the cylinder should also stay constant, right? So that's also stay the same. But the only thing changing is the area, right? Because when we're trying to find, the area of cylinder using multiple thin ring, right? So we have a thin ring right here. Then we just keep overlapping a bunch of thin ring until we get the solid cylinder. So now we have this formula. We can plug into your dm. So I is equal to the integral of r squared of rho l dA, right? Okay, so we know the area of a circle is a is equal to pi r squared. And then if we take the derivative of area, we get 2 pi r dr, right? Because the thin ring have different radius away from the axis of rotation. So we get this equation. So we plug it in. Dr. Again, now we have respect to r. We can pull out constant. So we want it to be in respect of r, so we can just pull out anything that is not r. So 2 pi, then rho, then the length, then integral r cubed dr, right? And then the bound is from the axis of rotation, which is 0, right? This is 0 on the axis of rotation all the way to the edge, which is a distant r away, right? So from 0 to r. So now you derive r cubed. The integral of r cubed is just r over 4, r to the 4th over 4 from 0 to r, which is 2 pi. That is just r to the 4th over 4 minus 0. then I'll expand rho into, rho is just mass over area, then area of a solid cylinder, that's just a circle times the length, so area is just pi r square times the length, then L, then R4 over 4. Right. So pi cancel out, length cancel out, this 2 cancel out with the 4, leaving you with 2. And then the R, 2 of the R cancel out. So you find, so your moment of inertia is m r squared over 2. Okay, so for part B, we're trying to find angular acceleration. So we know that net torque is equal to Fr, and that net torque is also equal to inertia alpha, right? So we can set these two equal to each other. So Fr is equal to I alpha. But then in this case, the force that's causing the solid cylinder to rotate is tension. So we know that then the weight is causing it to go down. So I'll write it first. So mg, the tension is pulling up, is equal to ma. So I'll isolate for t. So t is equal to mg minus ma. Right. So I'll write out, so tr, then I'll expand I. So inertia of a solid cylinder is 1/2 mr squared alpha, right? That's what we're trying to find. Then one of the r can cancel out. Right, and then I'll replace t with what we found. But then we want it to be angular acceleration and not just linear acceleration. So we know that A is equal to, okay, this is the radius of the solid cylinder, so that's a capital R, alpha. So I'll replace linear acceleration with what we found. So mg minus, right. Now I'll try to isolate for alpha. Capital M is the weight of the solid cylinder. divide both sides by the whatever is in the parenthesis. Right, so you get this equation. Then plug in the numbers. So the weight of the block is 3 kilogram times 9.8 divided by weight of the cylinder is 30, then R is 0.3, then weight of the block, and then R again, capital R. Right. This should give 5.44 rad per second square. So for part B, earlier we found that alpha is equal to 5.44 rad per second square. And to find the linear acceleration, we know that A linear is equal to capital R alpha, right? Because it's 0.3 meter away from the axis of rotation. So we plug that in. To get 1.63 meter per second square. Right. And then for part D, revolution after 5 seconds. Right. So we have junction theta is equal to initial omega t plus 1/2 alpha t squared. So we know that the system is initially at rest. So this is 0. Right, so we have junction theta is equal to 1/2 0.44 in 5 seconds, which give us about 68 rad. But then they want in revolution, so we know that 68 rads times then 2 pi is 1 revolution, so it is about 10.82. All right, so part E, the new angular acceleration. So we know that net torque is equal to Fr, then net torque is equal to I alpha. So in this case, we have a counterclockwise torque by the M1, and then clockwise torque by the 2 kilogram M2. So first, I'll write out the generic. You can set them equal to each other. And then, so T1 for block 1, and then distance of capital R away, minus the clockwise, which is T2. Okay, I'll treat the 2 kilogram as T2, and then lowercase r is equal to just the inertia of the solid cylinder, because the rod is negligible mass, have negligible mass. So 1/2 mr squared. Then alpha, what we're trying to find. So derive the tension. So we know that T1 is equal to mg minus ma from part A. Then T2, we'll assume that it's spinning counterclockwise, right? So T2 will be greater. then the 2 kilogram. So M2, wait, let me add subscript. Then minus M2G is equal to M2A2, right? So T2 is equal to M2A2 plus M2G. So now I'll substitute in of the tension. Right. M1G minus M1A1 capital R minus M2A2 plus M2G lowercase r is equal to 1/2 capital M of the mass of the solid cylinder capital R square alpha. And then now we want alpha, not the linear acceleration, so I'll change off the A. So A1 R alpha, right? They should all have the same alpha because it's the same system, same rotation. It's capital R because that's the distance away from the solid cylinder for the M1. And A2 is lowercase r alpha, right? Of the rod. That's the radius of the rod. So I'll substitute that in. Lowercase r. Okay. Factor the radius. R squared alpha. Okay. Now I'll try to I'll try to isolate for alpha. So okay. So you get 1/2 capital M R square capital R square plus okay, and then factor out alpha. Okay. Okay. So divide both sides by whatever's in the parenthesis. Okay. So we have this equation. Capital R minus M2 G lowercase r all over half capital M capital R square plus M1R capital R square plus M2 lowercase r square, right? And then I'll plug in all of the numbers. M1 is so 3, 9.8, 0.3 minus 2, 9.8, 0.03 all over 0.5 30, then 0.3 square plus 3.3 square plus 2, then 0.03 squared. And that should give you 5.08 rad per second. Okay, so earlier we found that the angular acceleration is 5.08 rad per second squared. Now we want the linear acceleration for m1. So we know that a1 is equal to capital R, right? Because that's the distance away from the solid cylinder. Then alpha. So I'll plug in the numbers. Which give you about 1.52 meter per second. All right, now we're trying to find the KE of the cylinder, and we know that it only have KE rod because it's stuck in place. So first we need to find the angular velocity after the travel distance of 5r. So the comments form. Initially at rest, so this is 0, so Vf is equal to radical 2a delta x, right? So I'll plug in all the numbers. 2. Then earlier we found a of m1 to be 1.52. Then delta x is 5 times r, which is 0.3, and this give you about 2.14 meter per second. Right, now we're trying to find omega, so we know that v is equal to, we're looking at m1, so it's the distance capital R away, and then omega. So omega is equal to v over r, which is equal to 2.14 divided by 0.3, which is 7.12 rad per second, right? So now Ke rod is equal to 1 over 2, then I omega square. That's how it's span on it. Inertia of the cylinder is 1 over 2 mr square, then r square, and then omega square. And now I'll plug in the number. Mass is 30 kilogram, r is 0.3 square, and then omega is 7.12 square. And then you get about 34.2 joules. So in part H, we're trying to find net work. And in this case, we know that net work is equal to change in Ke, right? So, which is equal to Ke linear of m1 plus Ke rod of the cylinder plus Ke linear again of the m2, the 2 kilogram, right? So now I span on it, so plus square plus 1 over 2 m2 v2 square, right? And then side work. So we know that omega is equal to alpha t. So omega at t is equal to 5 seconds is equal to, earlier we found alpha to be 5.08 times 5, which is about 25.4 rad per second, right? And then V1 is equal to capital R, right? We'll look at M1 and omega. They should all have the same omega. So V1 is equal to 0.3, then 25.4, which is 7.62 meter per second. Then V2 is equal to, now we'll look at the one on the rod, which is lowercase r, and then omega. Right, so V2 is equal to 0.03, then 25.4, which is equal to 0.762 meter per second. Okay, now back to the network formula. I'll just plug everything in. 3 kilogram, then 7.62 square plus 2 parentheses 1 over 2, and then mr square. M is just 30, r is 0.3 square, and then omega is 25.4 square, then 2, and then 0.762 squared, and this should give you 523.1 joule.